Boom. All right, Juliban, welcome. So this is still the voice of Juliban, and we're in the very last chapter of this amazing course. Okay, this amazing course came 122. We're in the last chapter, which is acid-base reactions. In the former chapter, we looked at acid, bases, and salts (ABS). Okay, so but there are some very brief revisions you need to make as far as AB reaction is concerned. At least the concept of acid and bases should be remembered. You talk about the definition of an acid according to Antoine. You talk about the definition of acid base according to Svante Arrhenius. You talk about Bronsted Lowry's definition. You talk about G.N. Lewis' definition. Okay, remember Antoine Lavoisier is on oxygen, and you talk about Vante Arrhenius is on hydrogen ion. That's the only replaceable ion when dissolved in water. Then you talk about Bronsted and Lowry, which is purely on proton donors and proton acceptors, and then on G.N. Lewis, which are on electron pair acceptors and electron pair donors, right? So let's go straight into the work, and that is the pH itself, pH concept. pH concept. Now, what is pH? pH was actually discovered by a scientist called Sorensen Peter Soren. Yeah, he has the flux symbol in the place of a O. Sorensen Peter Soren in 1908. That's about 101 years after John Dalton's postulations. Okay, so he came up with the concept of the pH so as to quantify the degree of acidity or basicity of substances. He was worried. Yeah, we know the strength of an acid, we know the strength of a base. How do we quantify the degree of acidity or the degree of basicity of a particular acid, as a case may be, or base? So he came up with the concept of the pH, of which he named potential of hydrogen. Others we call it pondus dihydronium, others we call it power of hydrogen. But those are personal definitions, and they are subject to whosoever that give those definitions. What we have here is potential of hydrogen. Potential of hydrogen. So according to him, he said potential of hydrogen being pH is the negative logarithm to the hydrogen ion concentration to base 10. And he also defined pOH as the negative logarithm of the hydroxide ion concentration to base 10 as well. His pH scale came up with 14 divisions. Yeah, 14 divisions. And the seventh division is the neutral point. Anybody that is below 7 is acidic. Anybody above 7 is basic. The first half is for acid. The second half is for basic strength. According to him, a pH between 1 and 7 is acidic. A pH between 7 and 14 is basic. While a pH of 7 is neutral. Right? So to him, the closer the pH value is to 1, the more acidic the substance is. The further away the pH value, or the closer away the pH value is to 14, the more basic. The closer it is to 7, the more neutral the particular substance becomes. Now, the big question is, how did he come up with these values of 7, 14, and all that? Now, according to Sorensen, he said, if the pH of a solution is the negative logarithm of the hydrogen ion concentration to base 10, same with the hydroxide ion concentration, then he took pure water as a sample. On studying pure water, he got to discover that the concentration of hydrogen ion in pure water is 10 raised to the power minus 7. He also discovered that the concentration of the hydroxide ion in pure water is also 10 raised to the power minus 7. And then he now imputed it into his formula. pH equals negative logarithm of hydrogen ion concentration to base 10. And at the end of the day, he got 7 as pH of pure water. And he did that for pOH. He also got 7 for pOH and came up with a conclusion that the algebraic sum of pH and pOH of a solution is equal to 14. And then the same thing happens with the concentration in terms of ions, that the hydrogen ion concentration times the hydroxide ion concentration will give you 10 raised to power minus 14. All right, so that takes us to the various facts we need to know as far as this chapter is concerned. We'll start with the very first fact there. Number 1, of course, pH is the negative logarithm of the hydrogen ion concentration to base 10, right? The minus can be removed, then you have 1 all over hydrogen ion concentration. That's the log to base 10 of it, still gives you pH. The pOH of a solution, which is basic now, is actually the hydroxide ion concentration. The log of the hydroxide ion concentration to base 10. Of course, we have discussed that before, but take note, these ones always work for strong acids, okay, and strong bases as the case may be. The sum of the pH and pOH of a solution equals 14, which we have discussed as well. The product of the hydroxide ion concentration and hydrogen ion concentration is 10 raised to the power minus 14 for strong acids, discussed as well. The hydrogen ion concentration in a given acid can be determined from the product of the concentration of that acid to the quantity of hydrogen ion concentration in terms of moles. What do I mean? If I have 0.2 molar of tetraoxosulfate 6 acid and you're asking me what is the concentration of hydrogen ion in 0.2 molar of tetraoxosulfate 6? That's simple. All I need to do is to find out the number of atoms or the number of moles of hydrogen ions present in tetraoxosulfate 6. In fact, the basicity, that's what we're talking about, which is 2. So 2 times 0.2, that will give me 0.4 molar concentration of hydrogen ion concentration. The same concept is applicable to the base. The hydroxide ion concentration of a base or an alkaline solution can be determined from the product of the concentration of that base and its acidity. Yes, the acidity of a base is simply the number of replaceable hydroxide ion concentration. The basicity of an acid is the number of replaceable hydrogen ion concentrations or hydrogen concentration in it. So if I give you magnesium hydroxide, for example, and I tell you that it's 0.3 molar, and I'm asking you to calculate the concentration of hydroxide ion in 0.3 molar of magnesium hydroxide, we know that there are 2 replaceable OH. So 2 times 0.3 will give us 0.6 molar concentration of hydroxide ion in 0.3 molar of magnesium hydroxide. So that takes us to the next fact. Now we go to the aspect of weak acids. Weak monobasic acid, especially acetic acid, hydrofluoric acid and all that, or hydrocyanic acid as well. Those are weak monobasic acids, okay? So the hydrogen ion concentration of a weak monobasic acid is simply the square root of the acid dissociation constant times the concentration of the acid. That is the square root of KAC. Ka, as I said before, is the acid dissociation constant, while C is the concentration of the acid itself, which is weak. Take note, Ka, acid dissociation constant. And the fact there is, acid dissociation constant actually is directly proportional to the strength of an acid. A strong acid has a very big acid dissociation constant, while a weak acid has a very low acid dissociation constant. So it's a direct proportionality. The bigger the Ka value, the more concentrated or the more acidic the acid. The same thing works with base. Ka is to acid, Kb is to base. So the base dissociation constant is also directly proportional to the strength of the base. So if you have a Kb of 10 and a Kb of 20, Kb of 20 is more basic than a Kb of 10 in terms of strength. That is what we're trying to say. All right. So that takes us to the pOH of a weak monobasic base. Monoacidic base, I beg your pardon. So the pOH of a weak monoacidic base is given by the negative logarithm of what? Of the Kb, the square root of KBC base 10. Now take note, you may be wondering where this concept of minus log of KBC base 10 is coming from. First and foremost, you have to understand that hydrogen ion concentration is equal to KBC. Hydroxide ion concentration is equal to KBC, while hydrogen ion concentration is equal to KAC. That's their square root. So you just substitute that in that formula and you will just be good to go. Next, for a polyprotic substance, when we say polyprotic substance, we mean substances that have basicities, or let's say acidic substances now, that have basicities that are greater than 2. For example, phosphoric acid or tetraoxosulfate 6 acid. So for such acids, Ka1 is always greater than Ka2, and Ka2 is always greater than Ka3. In other words, the first acid dissociation constant has a very high amount of energy required compared to the second acid dissociation constant. For example, phosphorus acid The first dissociation will give you H2PO4 minus. To remove that first hydrogen, you need more energy compared to removing subsequent hydrogen from it. And remember, H2PO4 minus is more acidic than HPO42 minus, and is also more acidic than PO4 3 minus. So acidity decreases, isn't it? So K1 is always bigger than K2. Very important. Very, very important. And that also leads us to the next part, which is the pKa and pKb. Now, but before we talk about pKa and pKb, it's important for you to note that the product of the acid dissociation constant and the basic dissociation constant is equal to the water dissociation constant. That is pure water dissociation constant. What we mean is that Ka dot Kb is equal to Kw. And Kw we know is 10 raised to the power minus 14. So if you have Ka, you can easily get Kb. And if you have Kb, you can easily get Ka. Remembering the fact that their product equals the dissociation constant of pure water. So that takes us to pKa and pKb. pKa is potential of acid dissociation constant. pKb is potential of base dissociation constant, right? Now, but these potentials we are talking about are on a logarithm scale or on a pH scale. Just like Ka is to concentration of hydrogen ion, so is pKa to pH. So on a pH scale, what is Ka on a pH scale? That's Kpa. So potential of acid dissociation constant, right? So the potential of acid dissociation constant is simply the strength of an acid in a logarithm scale, while pKb is simply the strength of a base in a logarithm scale. No wonder pKa is equal to the negative logarithm of the acid dissociation constant to base 10, while pKb is the negative logarithm of the base dissociation constant to base 10 as well. And also, very, very importantly for you to remember, the relationship between pKa and Ka is an inverse proportionality. That means the higher the pKa value, the weaker the acid. The smaller the Ka value, the bigger the pKa value. So if a small Ka value represents a weak acid, automatically that weak acid will have a big pKa value. That pKa value can be big, maybe very close to 7. You get the point? Good. So just know that pKa and Ka are inversely proportional. The same thing applicable to Kb and pKb, inverse proportionality. Next, the degree of hydrolysis. This is HW now. I say HW. KH. KH is hydrolysis constant, right? So the degree of hydrolysis of a substance is given by hydrolysis, which is the square root of KH all over the concentration. KH is the hydrolysis constant. The C is the concentration of the solution, as the case may be. So a relationship between Ka, KH, and Kw. KH is just taking the place of Kb. You already know that Ka dot Kb is equal to Kw. So for the presence of KH, it is KH dot Ka equals Kw, right? Very important. So if you want to calculate the hydrolysis dissociation constant when you have the acid dissociation constant, just take 10 raised to the power minus 14 divided by Ka, and you get your value straight away. The last fact I'm going to give you on pH is simply based on the percentage ionization of weak acids or weak bases. Percentage ionization of a weak acid is simply given by the square root of the KAC divided by the concentration times 10 raised to the power 1 times 10 times 100 all over 1. How do we mean? It's just like saying KAC, that's the square root of KAC divided by C times 100 all over 1. That is for acid. For bases, you have KBC, that's the square root of KBC divided by C times 100 all over 1 as well. We do not talk about the percentage ionization of strong acids. We focus on weak acids because strong acids ionize virtually completely. They have almost 100% degree of ionization. So there is no point calculating their percentage ionization. But for weak acid and weak bases, they have very little level of ionization. And because their degree of ionization is small, hence the need to know how small the degree of ionization is. Then you apply the formula. So basically that is that for pH. I'm going to cut the audio short here because I don't want it to be too long. So, but before I end this audio, let me just ask you some few questions, provide answers to them. Number one, calculate the pH of an acid whose hydrogen ion concentration is 5 times 10 raised to the power minus 9 molar. Of course, you can do that, right? Just apply the negative logarithm of the hydrogen ion concentration and you'll be good to go. So the next question on my list here says calculate the pH and pOH of 0.002 molar of H2SO4. You're given H2SO4 and you're given the concentration. For you to get a pH, you have to first of all know the amount of concentration of hydrogen ion inside tetraoxosulfate 6. So that's 2 times 0.002. Once you get the concentration of hydrogen ion, you can get a pH. And once you get a pH, you can get a pOH. As simple as that. The next one says calculate the pH of 0.004 molar solution of acetic acid, given that the Ka of acetic acid is 1.8 times 10 raised to power minus 5. So you are giving me Ka and you are giving me concentration. You are asking me to calculate pH. Simple. pH is simply the negative logarithm of the square root of KAC base 10. And I am good to go. Just like that. Then the last question I may ask you for today is simply to calculate the pKa of a 0.05 molar of angelic acid whose pH is 4 at 25 degrees Celsius. Calculate the pKa of angelic acid. If you're asking me to calculate pKa, all I need to remember is that pKa is the negative logarithm of the Ka concentration to base 10. First, I need to know the Ka concentration of angelic acid. Now, if the question didn't give you the value of Ka of angelic acid, it is your duty to look for it. So how do I look for it? You were given pH, right? And you were given the concentration, right? And you know that pH is the negative logarithm of the square root of KAC base 10. So just make Ka the subject of the formula and boom, you're good to go. Now take note, once you get the value of Ka, you can get the value of pKa, because pKa is the negative logarithm of the Ka concentration to base 10. Also take note, angelic acid is a weak acid, very weak acid. In fact, it's an acid gotten from roots of carrots. Angelic, from the word angel, not demon, was actually discovered in Angelica. It's the name of a country, and so it was named after the country where it was discovered to be angelic acid. But it's an acid gotten from roots of fruits like carrot or something. All right. So I think that settles that question. Just the last question. Calculate the percentage ionization of ethanoic acid in a 0.5 molar solution of ethanoic acid if the Ka is 1.8 times 10 raised to power minus 5. Simple. I have Ka, I have concentration. Just substitute in percentage ionization, which is square root of KAC all over C times 10, 100 all over 1. Boom. All right, in the next class, we're going to look at buffer solutions. We're going to look at common ion effect, and then we are also going to look at solubility constants and finally precipitation. Boom.